classify each of the following batting averages as either unusual or not unusual. Okay, so this first one is we have a score, and for all of this, for this assignment and for this unit actually, and a really important equation to remember is the z-score equation, which is x, which is your observance, minus your mu, which is your population mean, divided by sigma, which is your standard deviation. We'll go over that more, but I'm going to leave that up so you can always remember that this is really important. Okay, so this first one, the batting average was 0.190. Okay, so we're going to check this out by plugging in 1.90 minus the population average, which is 0.261, or 2.61, excuse me, divided by the standard deviation, which is 0.034. Okay, so if you plug that into your calculator, you come out with a value of negative 2.088. Okay, so what that means is that this batter bats 2 standard deviations less than the mean. Okay, and so we would call that unusual. Okay, so this is the same process that we're going to go through for the next, for the following ones as well. Okay, so if you were batting a 2.55, our equation will look like this. Okay, so notice these two numbers are the same. This is your population mean, and this is your standard deviation of the population, and these are the individual scores that we're looking at. Okay, you throw this into the calculator, and you get a z-score of 1.118. Okay, or in other words, just one standard deviation above the average this guy is batting. So that's not unusual. Okay, and for C and D, you just replace this number. For C, you replace this number with 0.325. And then for D, you replace this number with 0.335. Okay, anything above 2 standard deviations we consider unusual. Okay. Question 2. Find the probability that a randomly selected professional baseball player will have a batting average that is greater than 0.335, or 0.335. Okay. Okay, so this one, we got to find that z-score. We have to find this how far of a standard deviation that is away. Okay, so we have, or how many standard deviations away he is from the mean, excuse me. So we're going to start with our z-score. So a z is equal to that observance that we're looking at, the 0.335, minus the average or the mean, which is 0.261, divided by the standard deviation, which is 0.034. Okay, so you type that in and to your calculator, and you come out with 2.176. So we have z-score of 2.176. Okay, so with that z-score, we're going to use that z-score and come over to the normal probability applet to find out what the probability of getting above that. So we're here at the normal probability applet. Real quick, if you want to remember how to get to that, you come to the main page of statistics.byuimath.com. Go to your course resources, which is the first link, and then down to this second to last normal probability applet. Okay, these bottom things right here are your z-scores, and we had a positive 2.176. And you hit enter, and this blue area shows the probability of getting above. Okay, now we're not worried about who gets below, we're just worried about who got above. Now the area of the blue is represented in number form up here at the top under area, which is 0.0148. Okay, or in other words, 1.48% are greater than 0.335. Question 3. Provide a brief description of a normal density curve. Describe the shape and the properties. Okay, so the normal density curve, for example, like the normal probability applet, is symmetric, meaning it goes down and slopes on the right and goes down and slopes on the left as well. Or sometimes we refer to that as bell-shaped. It is also determined in the middle, defined in the middle by the mean, and then as the distribution we define by the standard deviation. Question 4. In the following z-score formula, please state what each symbol stands for. Okay, so we're going to kind of review for just a second what each of these symbols in the z-score means. Okay, so starting here, your z represents the how many standard deviations away from the center you are. So if you get a -2, that as a z, that means you're 2 standard deviations to the left of the mean. Okay? Your x is your observed value. Okay? Or in other words, it's what you're concerned with. In the batting averages, these were the individual scores we were looking at. So the last question asked, what's the probability of batting above 0.335? Okay, so that 0.335 was this x value. Your mu is the mean of the population. Okay, so for in the baseball, it was the mean or the average professional baseball player bats 0.261. The batting average is 0.261. And then this sigma down here at the bottom is the standard deviation of the population. Okay? So that is the z-score formula. Question 5. In no less than 3 sentences, please define and describe the 68, 95, 99.7 law. Okay, so this 98, 95, 99.7 rule is something that's really helpful. And I'm going to use kind of a graphic of the normal probability applet to describe it. Okay, so we have our mean here, and let's pretend we're talking about test scores. Okay, and let's say that the average test score was a 75. Okay, and our standard deviation was 5. Okay, so we have 5 up would be 80, and a score of 80. Now remember the z-score right here, not to be confused. So the z-scores, which I'll draw a little bit to the left here. So remember, your z-score of 0, when you're doing the z-score, gives you the mean. And then this is 1, and then 2, which would be a test score of 85. And then a z-score of 3 would be a test score of 90. Okay? And in the same way, so for a -1, -2, -3, on the z-scores, we'd have a score of 70, a score of 65, or a score of 60. Okay? Now, what the 68, 95, 90, 99 rule says is that 68% of the students will score, or scored, between 70 and 80. So you can say that 2/3 of the class, a little more than 2/3 of the class, scored between 70 and 80. So they got a C. 2/3 of the class got a C. Okay? And then if you add in, and then you can say also that 95% of the students, so if you include this another -5 and +5 to bring us up from 65 to 85 on the scores, this group of students, 95% of the students got between these two scores. And then you can say for the 99 that 99.7% of all the students scored between 60 and 90. So that's kind of a visual representation of what the 65 or 68, 95, 99.7 rule represents. Question number 6. Scores on the quantitative portion of the GRE are approximately normally distributed, with mean mu equals 150.8 and standard deviation of sigma equals 8.8. Okay, those first two numbers are pretty easy to get. They just come straight from the chart right there under the GRE scores. Okay. Now, part A says what proportion of the people who take the quantitative portion of the GRE will score above 165. Okay, so if you remember our z-score up here, the formula, we're going to use that to solve this question out. So our 165 is the score that we're looking at. It's the observed score that we're going to be testing, minus the mean, the mu, which was 150.8, divided by the population standard deviation, which they told us was 8.8. Okay? So when you plug that in to the calculator, you come out with 1.6136. Okay? And then in order to find out what proportion of the people who take the GRE will score above that, we're going to take this z-score and we're going to plug it into the normal probability applet. So here's the normal probability applet, and if we plug in the z-score that we just got, the 1.6136, we get, and we want to make sure that we shade this upper portion because we want to know those that scored above that, then we get 0.0533. Okay, so that area represents the percentage or the proportion of people that served, or that, that received a score higher than 165. Question B. If a student score is in the 10th percentile, what would their corresponding z-score be? Okay, so this one is actually found by just simply using the applet. So over here on the applet, first let's highlight the area that we're looking for. We are looking for the 10th percentile. So we know that's going to be less than half. So we only need this very bottom one. And we're going to be typing in the area that we're looking for. Okay, that 10.10, which represents the 10%. So these group right here scored they are the lowest 10%, or the 10th percentile. Okay, so in order to find the z-score, we just type it in there and it pops out right here. So the z-score is -1.282. What is the quantitative GRE score for a student who scores in the 10th percentile? Okay, now we're going to take that last question and take it one step farther. So we have our classic z-score, but now we have the z-score and we have the z-score, but we're missing the value. That's what we're looking for. What did that 10th percentile student score? So we type in we input what we know. And we know a few of these values. So we know that the z-score is the -1.2282 is equal to, we're going to be solving for x, and we're going to minus the mu, and the mu hasn't changed, so the mu is still 150.8. and the standard deviation is still 8.8. So as we rearrange this equation algebraically, we're going to bring across the 8.8. So then we have just x equals minus 150.8. And you add that over, and I'm just going to switch the sides. Well, and so we'll get 8.8 times negative 1.282 plus 150.8 is equal to our x. Okay? You plug this part into your calculator, and the score is 139.5. Question 7. The mean speed of hydrogen at room temperature is 1,800 meters per second with a standard deviation of 600 meters per second. Part A. At room temperature, the mean speed of hydrogen particles is approximately normal with a population mean of mu 1,800 meters per second and a standard deviation of 600 meters per second. Okay, now remember that those are the values that were given to us in the problem. Part B. What is the probability that a randomly selected particle has a speed of over 2,500 meters per second? Okay, so now we're going to come back to our z-score formula. We're going to look for the z-score because we need a z-score in order to plug it into the normal probability applet. So our z-score, our value that we're looking at is 2,500. We want to know how many that the particle has a speed of higher than the 2,500, minus our mean, which is 1,800, divided by our standard deviation, which was 600. Okay, so we plug that into the calculator, and we come out with 1.16. Okay, so now this is our z-score. Okay, so they scored 1.6 standard deviations above the mean. Now, if you think about it, this makes sense. Let's just break this down just for a second here. If our mean is 1,800 and one standard deviation, which would be a z-score of 1, is 600, then if you went 600 above 18, you'd be at 2,400. And we were at 2,500. So the fact that we got a little bit above 1 should make sense. Okay, now we're going to plug that into the normal probability applet. So we come over to our applet, and this time we're concerned again with which is faster. We're looking for a faster speed, and so we're looking for this portion right here. And we need to type in our value of 1.1667. Okay. The corresponding area, which also represents the probability of randomly selecting a particle with speed faster than 2,500, is 0.1216, or 12%, or say about 1 in every 8 or 9 times. Question C. What is the probability that a randomly selected particle has a speed that is less than 2,500 meters per second? Okay, so our probability that it was probability that it was faster from the last question was 0.1216. And what's cool is that if you remember from our rules about probabilities, the probability that it was slower is just 1 minus that number. Okay. And so the answer there is just simply 0.87. Okay, and that is a simple way to find, because remember, the probability that it is 1 minus the probability that it's not. And in an earlier example, we talked about dice. The probability of rolling a 5 on a dice is 1/6. The probability of not rolling a 5 is 1 minus 1/6, which is 1/5. Good. Okay, D. What is the probability that a randomly selected particle has a speed that is less than 1,500 meters per second? Okay, so we're going to run a z-score again. Hopefully this is becoming pretty second nature. So 1,500 minus our mean of 1,800 divided by our standard deviation of 600. Okay, that gives us a z-score of negative 0.5. Okay, that makes sense. You get negative 300 divided by 600. It's negative 1/2. Okay, so we're going to take this z-score and plug it into our normal probability applet. And this time we're wondering what the probability of getting less than 1,500 is. So we're going to select our small area there, our low one, and plug in negative 0.5. Okay, we have an area of 0.3085, or in other words, a 30.8% chance of selecting a particle at random that has a speed less than 1,500 meters. Part E. What is the probability that a randomly selected particle has a speed that is between 1,500 and 2,500? Okay, so we're going to kind of show this graphically. I think this will help you visualize how this is going. So our probability here at the beginning that a particle would have lower than 2,500 was 0.8783. Okay, so this whole area from here to there was 0.8783. Okay, now we did another one and we found that the 1,500 mark was about right there. And the value in this area, right here, the smaller area, was equal to 0.3085. Okay, so we have this whole one and then a small one. Now what we're looking for in this problem is how many particles are in between those two values. Okay, so since we have the big one, we're going to take the 0.8783, and then we're going to subtract off this part because we're not worried about these people. So it's minus 0.3085. Okay, so you subtract that, and you get your answer to be 5698. 0.5698. Okay, and that right there is the probability of finding a particle between 1,500 meters per second and 2,500 meters per second. Question F. What is the third quartile of the speeds of hydrogen at room temperature? Okay, so now remember, the third quartile is the 75th percentile, and up here in our applet, the 75th percentile can be represented by an area of 0.75. Okay, so we have this area of 0.75. Now, since we're looking for a value, we're going to take this z-score and we're going to move it into our formula. Let's erase this. So our formula is as follows. We have our z-score of 0.6745 is equal to our x value, which is what we're looking for, the x value at the 75th percentile. Remember, this z-score represents the 75th percentile, minus our mean, which is the 1,800, divided by our standard deviation, which is 600. Okay, you do your algebra and you get x is equal to 600 times 0.6745 plus 1800. Plug that into your calculator and you get x equal to 2204 meters per second. Okay, now remember that represents the third quartile, and that third quartile means that 75% of the particles are as slow or even slower than 2204. Okay. Okay, now these plots. Okay, plot A is obviously not normal. Plot B is also not normal. That little S curve disqualifies it from being normal. C is normal. Now, although it's kind of got some bumps in it, the bumps are consistent, and you could draw a line through it, and there would be even dots above and below the line. So we consider that normal. D is normal, nice and straight. E is also normal, and F is the most normal of them all.